Okay, so from our lesson yesterday, we did the derivation of the time dilation equation. And if you recall, what we did is we started out by just taking the perspective of the person inside the ship, where we fired a laser beam up and then back down. We found that the distance it covered was 2 times 2d divided by the speed of light, told us the time. Now we know that that distance that it traveled was clear, and that the speed of light is always constant at c, and so therefore the time that we get is with respect to the person that's stationary inside the ship. Yesterday we called it delta ts, or it could be done as delta t prime. They're both the same thing, different notations, different books use different notations. But what we'll say is we'll call that the delta ts. Here is our proper time. So if the notation yesterday used was t prime, we're going to change it for consistency to be ts for this note. And then tm was known as the dilated time. And it's measured by the person who's observing the motion of the ship. So they're outside of the event. Okay, so you'll often hear something like moving clocks run slow, and that's because no matter what, and we pointed this out yesterday, no matter what we do, delta Tm is always going to be greater than or equal to the proper time. Now the only time it's equal to it is, of course, if the speed is 0. And that's the only time that the two times would ever match. So from the derivation, we said in the stationary point of view, we could find the time it takes for the laser beam to go up and back down. From the person watching the event from outside in a ship that's moving very fast, the laser beam will go on a diagonal up and a diagonal down. And recall that because the speed of light is constant, it doesn't get added to the speed of the ship, so it has to travel further. Well, if it has to travel further, but the speed isn't adding due to the original momentum of the ship, and it's always staying at the speed of light, it must cover that longer distance in the regular time it would take the speed of light to do that, which means it takes longer. So you measure a dilated time. And that's why this time difference occurs. We then used Pythagorean theorem, did a substitution, and we got this equation. Now you'll notice here that there's another little piece to this. And what we did is the equation you had from yesterday is delta Tm, the dilated time, is the proper time divided by the square root of 1 minus v squared over c squared, where v is the speed of the object, c is the speed of light. I've written here, this can be written in two different ways. This is a little gamma, okay? And this is just really an interesting point to make here. This gamma here is called the gamma factor. You'll see it often when you're talking about quantum physics or special relativity. Gamma equals, that's another way to write it. This is the computer's version of it. Gamma is equal to 1 over the square root of 1 minus v squared over c squared, like that. Okay? And what you'll see from that is that if you take this and multiply by delta ts, you get this formula. So all it is taking that little piece out and calling it gamma. Now there's a reason why we do this, because it makes calculations a lot nicer to do. So for instance, on the top we have the numerator is 1. And an interesting point is that no matter what, on the bottom, no matter what you put in for v, if you start it with 0, it equals 1. Okay? But if as v starts to get bigger, v divided by the speed of light is a smaller number. 1 is a number, and 1 subtracted number means that this is less than 1. Okay? So the bottom part of this, and then you square root it, is just always going to be less than 1. And because the bottom is always less than or equal to 1, this implies that if you take 1 and divide it by any number, like say 0.9, it gets bigger. If you divide it by 0.8, it gets bigger. Any number you divide it by, if it's less than 1, this number at the top will always get bigger. So what it means is that gamma is always greater than or equal to 1. And that's an important point to make. That gamma factor, the multiplication factor, so it's like a multiplication factor, the gamma factor, is always greater than or equal to 1. If the object is not moving, at v equal to 0, gamma equals 1. At v equal to c, now here's an interesting case. If the speed of the object is the speed of light, look at this equation. C squared divided by c squared is 1. 1 subtract 1, 0. Square root of 0, 0. 1 divided by 0, gamma becomes infinite. The multiplication factor for the time dilation becomes infinite. So the closer and closer you get to the speed of light, this number, the gamma factor, gets bigger and bigger, which means that the amount of time that you see going by gets bigger and bigger. So at really fast speeds, the time you measure from inside the ship gets multiplied by great factors. So the person outside of the ship is going to see a larger time go by. So you might, on the ship, only measure 10 seconds go by, and the person outside measures 3 minutes go by. You might travel out in space for a year, and when you come back, everybody on Earth has aged by 3 years, if the gamma factor were 3, for instance. Well, how relevant is this in terms of, what point does the gamma factor play a role? So another way of looking at this, and we'll look at a little relationship here. We've got a scale here of the gamma factor. Down here we have a speed as a percentage of c. So this is 0.1 times the speed of light, 0.2, 0.3, 0.4, you get the idea, all the way up to the speed of light. Or 10% of the speed of light, 20% of the speed of light, 30% the speed of light, so on and so forth. Over here we have the gamma factor. It starts at 1. Okay, this is the important, this is the one there. Now, you'll see that they've written the gamma factor like this. They wrote it as gamma equals delta t prime, which is the stationary time. Sorry, they wrote it as delta tm divided by delta ts. They've actually used different notation than we use. So it's delta tm over delta ts, which comes from over here, okay? Which comes from the very top part. Comes from this first piece here, which says the gamma factor is equal to that, yes. Or the gamma factor is simply a ratio of the delta tm, the dilated time, divided by the proper time. So if the proper time is 1 second and the dilated time is 5 seconds, 5 divided by 1 means there's a gamma factor of 5. You could put that over here, you could rearrange this formula and find the speed of the object. There's lots you can do with this. So there's different ways of representing gamma, and then here what they're doing is they're showing the effects. And what you'll notice is that up till about even 0.3 times the speed of light, so when you're at 30% the speed of light, and that's incredibly fast, gamma is approximately equal to 1. It's unnoticeable. For all intents and purposes, you wouldn't notice anything. Even if you're at 30% the speed of light, you're probably not going to notice the effects of relativity. You're not going to see the times dilate very much. From about 0.3, these are just subjective ranges. From 0.3 to about 0.6, your gamma factor is getting just a little bit bigger than 1. Just slightly bigger than 1. This would be, subjectively somewhat noticeable. Once you get into this realm of 0.6 to say 0.9, we would say that's noticeable. But look at, even at 90% the speed of light, if you follow this across, our gamma factor is like 2.1. So if a person flew out into space on a rocket ship at 90% the speed of light, which is unbelievable to even think about how fast it is, if they left for 1 year, right here, 1 year, and the gamma factor is 2.1, that means that the dilated time, the people on Earth that they left behind would age by 2.1 years or around there. So it's not a huge difference, even at 90% the speed of light. We're only getting a factor of 2. Their clocks would be a year apart, and if they were twins, let's imagine that a twin flew off at 0.85 the speed of light, where the gamma factor is 2. If they left for 10 years, when they came back to Earth, the people on Earth would have, their dilated time, they would have measured 20 years go by. So they would appear to be 20 years older, and the person that left on the ship would only appear to be 10 years older. Now it gets crazy. Past the 90%, you can see that this is an asymptote. It's asymptotic. And it's the cosmic speed limit, which is the speed of light. Obviously, a gamma factor of infinity doesn't make any sense. The universe would sort of stop. We can talk about that later. But, you know, if you're getting very close to the speed of light, you can get a gamma factor of 9, of 10, and ever so closer, like every little minuscule amount more that you go closer to the speed of light, it jumps and jumps and jumps. So, I mean, this is very relevant for particle physics. Less relevant for our everyday life because we live in this realm way over here where the gamma factor is, you know, basically 1. So we don't get upset when people go in a car and they measure 10 seconds to go by and they say, come over to my house. And on my clock it says 10 seconds to get there. And the other people are like, oh, it took you 10 seconds to get here. Because the gamma factor is 1. Whereas were you able to move at the speed of light to move to your friend's house, it may take you, let's say they're really, really far away, they're past the sun, let's say, no, not past the sun, but just let's say they're just past the moon somewhere. It takes them 10 seconds to get to your house. You might measure, and if they're going, you know, double the speed of light, you might say, hey, why'd you take 20 seconds to get here, for instance. So what we're going to see now is representing speeds. I'm just going to show you a little trick here for representing speeds that will be helpful for you. Representing speeds. And for example, if I say that something is flying at 0 or moving at 0.75 c, that's the same thing as saying 0.75 times 3 times 10 to the 8. So if I put that in the calculator, I would say 3 exponent 8 times 0.75 is 2.25 times 10 to the 8 meters per second. Conversely, if I said something was traveling at 1.5 times 10 to the 8 meters per second, it's much easier to work in terms of c. So what I could do is I could take 1.5 times 10 to the 8 divided by 3 times 10 to the 8, which is the speed of light, and that would equal, I think you can tell what it's going to equal, 0.5 c. So you're traveling at half the speed of light. Using it in terms of c is very, very handy. It makes calculations much simpler when you're dealing with the gamma factor because you can substitute the values in very nicely. Let's do a very quick example of how to do this, just so that you're clear of what to do. So I'll do the first one for you. You're going to work through these problems here based on what I just do now, and you can use these sort of examples, the one I'm going to do here, at this point. So Einstein gets into a ship and travels at 0.7 c for 5 years. So the speed of the ship is 0.7 c, and travels for 5 years. He leaves a friend behind that started their clock at the same time. Upon return from his travels, how many years would have passed on Earth? So the person in the ship is measuring the proper time. So this is proper. And the person that's on the Earth that they left behind is going to measure the dilated time. Okay? Now, remember, moving clocks run slow. You'll often hear that. This is the moving clock. It sees 5 years go by. It's running slow, so the people that are watching it are going to see it take longer. So that's something you can kind of think about, just moving clocks run slow, and think about it in terms of the dilation. So the proper time, delta TS, is equal to 5 years. Like so. How much time passes on Earth? And basically, that's all we need to know. So we can do this in a couple ways. We can calculate the gamma factor and go from there, or we can use the equation right out. Since we're just looking for delta Tm right away, it's delta Ts divided by the 1 minus v squared over c squared. So that equals delta Ts is 5. Now the units, we can just leave it in years. We don't need to put it in seconds or anything. Divided by the square root of 1 minus. Now v squared is 0.7 c squared divided by c squared. Now here's the reason we did this. Turns out nicely that if you multiply the square into both terms right here, you'll see that this becomes 1 minus 0.7 squared, because the c squared and the c squared divide out, and then all you're left with is the 0.7 squared, like so. Putting it in your calculator, it's going to take practice. And don't forget the square root. And you get about 7 years pass by. So Einstein would be out there for 5 years. You would measure on your clock that an extra 2 years went by during that time, which is very strange. What's the gamma factor for this? Well, the gamma factor can be done 2 ways. You can calculate it like this. Which is the way I originally did it. So I would do 1 divided by, I usually do 1 subtract 0.7 squared, square root, take the inverse, and I get 1.4. So it's got a gamma factor of about 1.4. So if I took 5, times it by 1.4, I get 7. If I do 7 divided by 1.4, I get 5. So it's really interesting to think about the gamma factor. And remember, that's a ratio of the delta Tm over delta Ts. So 7 over 5 gives you the 1.4. So knowing the gamma factor is nice because it's just a multiplication factor that helps you with that. So I mean, you could have seen that up there. We'll do one other example, and then you can try the rest on your own. Or I'll get you started on this one. An astronaut travels into space at 0.99 c. Upon return to Earth, he realizes that the clock he left behind when he departed says he was gone for 3 years. So we see the speed is very fast, 0.99 c. So we're in the high gamma realms. The clock he left behind said he was gone for 3 years. So that's going to measure a longer dilated time. So we know that the time he was on the ship for him was going to be less, because remember that delta Tm is always going to be greater than or equal to delta Ts. We know that. How long would the clock on his ship indicate he was gone for? Okay, so in this case, we've got delta Tm equals delta Ts divided by 1 minus v squared over c squared. So there's a couple ways you can solve this. We can do it as a gamma factor, which many of you will probably find easier. Or we can rearrange this formula for delta Ts. So one way is to say, okay, delta Ts is delta Tm times this whole bottom piece, which is 1 minus v squared over c squared. This is always less than or equal to 1 So when we multiply it by any number, that number is going to get smaller. We can see that. So we type in 3 years, 1 minus, and again we've got it in the nice form of 0.99c, so that means the c squared and the c squared divide out. So you can write it in the simplified version like this. You don't want to plug in, convert it to 3 times 10 to the 8 times 0.99, square it, divided by 3 times 10 to the 8 squared, just to get the same result. It's extra work, and you don't need to do it. So I go 0.99 squared plus 1, or sorry, 1 subtract that, and then what did I forget here? Something called the square root. Don't forget that. 0.42 years. Just less than half a year goes by. So that person was out in their ship, what they perceive, or what they actually were out there on their ship for only 0.42 years, and the other people on Earth measured 3 years go by. So to do this with the gamma factor, you could have set this up. We could have calculated the gamma factor, and the gamma factor for 0.99c is pretty big actually, as you can see from here. 1 minus 0.99 squared. So 1 minus 0.99 squared, square root, and then find the inverse of it, is 7.0888. That's the gamma factor. So it's a high gamma factor. And if you look at the previous page, if you look at this page here, at 0.99c, 7, if we go across, it's about 99% the speed of light. So it makes sense. The result that we get looks very reasonable. You could even just, if you look at the speed the object's moving at, you can use this chart to figure out the gamma factor without even using the formula. It's not as accurate, but you can do it as a check. So if the gamma factor is 7, then we would just say, oh, I know that the time has to be smaller, so we take 3 divided by 7.0888 is 0.42 years. We get the same exact result. So what I'm going to suggest you do questions 1, 2, 3, and 4, and then finish off this sheet with 3, 4, and 5. We'll talk about the cosmic speed limit later. It's on the website as well. But really make use of the gamma factor. Really think about which is the proper time, which is the moving clocks run slow time, and the dilated time. And if you get it backwards to what you think it should be, obviously you mixed up the TM and the TS. So you're going to try these, and we'll take them up tomorrow and check how you did with them.